Okay, I want to talk a little bit about the formation of solutions and the factors that affect dissolving. And again, you need to understand how things dissolve so that the factors that affect dissolving make some sense. First of all, just appreciate what's going on here. When you are dissolving something, if this is my solid, if this is salt, these are sodium ions, they're positive, these are chlorides that are negative. Turns out water is what's called a polar molecule. It has a positive and a negative side. The hydrogens are slightly positive and the oxygen is slightly negative. So what ends up happening is the negative ion, the chlorides, are attracted to the hydrogens, and the positive sodiums are attracted to the negative oxygen. So what ends up happening is those ions kind of come in, attach, pull those ions in, and then surround them. Let me show you what that might look like. As you pull these in, here's this would be a chloride ion. Notice how it's oriented with the positive hydrogens toward the ion, and it gets surrounded. That process is called solvation. It's being surrounded by the solvent particles. Over here I have the positive sodium surrounded by the water molecules, but notice how all the molecules here are lined up so the negative oxygen is facing them. So what happened basically is the waters were able to come in, depending on which side is which here, would line up, attach, and pull these things in and then surround them. And that's kind of how things dissolve. Notice, and this is a very important point to pick up on, for this to dissolve, the solvent and the solute both had to have charges. The negative and positive things are attracted. Remember, opposites attract, and that is how these dissolve. There's a phrase, like dissolves like, which describes this. Things with charges dissolve other things with charges. Things without charges dissolve other things without charges. And that's a very important concept in terms of dissolving. So recognize that attraction between the opposite things. If your solute and solvent are similar, they both have charges, then you'll get dissolving. Actually, let me jump back there to this one. And again, this is just showing you how the ions break apart and separate into the sodium and chloride ions in solution. Again, here I'm just emphasizing the orientation. Notice I have a positive sodium here and the negative oxygens are lining up and kind of bonding to that. So this interaction is called solvation, which I mentioned. Water is one of the most common solvents, so there's a specific term for it. When you dissolve with water, it's oftentimes referred to as hydration. You're hydrating the ion, you're getting water in there as you do this. Now we're going to talk more about this down the road, but recognize just two small facts, and this may explain some things you've seen. Energy is absorbed when the bonds between the solute and solvent break. What that's saying is it takes energy. If you have sodium chloride, to separate the sodiums from the chloride takes energy, and that makes sense because they're attracted to one another. They have opposite charges and they're attracted. Now, when they then attach to the water molecule, that releases some energy. So when new bonds are formed between the solute and solvent, energy is released. When you break the original bonds between the solute and the solvent, like breaking apart the salt crystal, that always requires energy. Now what's interesting is when you dissolve some things, the solutions get very hot, some things get very cold, and that's explained by this. If you've ever injured yourself and a trainer gave you a bag where they smashed a little pouch of water and shook it up and handed it to you, it got very cold. What was happening is there's ammonium nitrate in there dissolving, and it takes more energy to separate the ammonium nitrate from the other ammonium nitrates, to separate the ammonium and nitrate ions, than comes out when the ammonium and nitrate attach to the water. So what happens is more energy goes into breaking the original bonds than comes out, so it's endothermic, and that's why those bags get cold. There's some other things we've dissolved in class, like sodium hydroxide in water, where the solution got very, very hot, and that's caused by the fact that the attraction between the sodium and the hydroxide to the water is greater than the sodium and hydroxide ions to each other. So more energy comes out when the new bonds are formed, and therefore it's exothermic and energy is released. So you may have noticed that when things dissolve that you get these temperature changes, and that's what's going on. Now, the solubility is the amount of solute that can dissolve at a given temperature, and I want to focus on factors that affect that, and that's kind of an important thing. In this case, this shows you a graph where pressure affects the solubility of gases, and you've seen this in a soda, and I'll talk more about this in a moment, but notice as the pressure goes up, the amount of oxygen I can dissolve also goes up. A good example, like I said, is a soda. If you've ever opened a bottle of soda that was clear, you may have noticed the minute you opened it, all these bubbles appear. One of the factors that affects solubility is gases are very much affected by the pressure. The higher the pressure, the more collisions that gas is having with the surface, the more particles get trapped and the greater stuff you have dissolved in there. The lower the pressure, the more easily the gas can escape from the liquid, and then you have lower solubility. So one of the factors, and we'll talk more about this in a moment, is pressure affects the solubility of gases in a liquid, and you'll see that here, that if I double the pressure, I double the amount of oxygen I can dissolve in water. So it's just a graph showing you that. Now, let me just go through these factors kind of one by one. The general rule I mentioned a moment ago is like dissolves like. Things that are polar, things that have a charge, will dissolve other things that are either ionic or polar. Polar and ionic both mean you have charges. Non-polar things will dissolve other non-polar or molecular things. Molecular things are generally considered to not have a charge. Now some of them do, but for the most part they don't have charges. Things without charges dissolve other things without charges. Things with charges dissolve other things with charges. So as an example, iodine, and this is going to come up in the packet that you do, iodine is molecular, it's balanced, it has no charge. Carbon tetrachloride is very balanced, also has no charge. So iodine will dissolve in carbon tetrachloride. Salt is ionic, has charges. Water is polar, we've said, has charges. So salt will dissolve in water. So salt is ionic, water is polar. So they will dissolve. Now, iodine has no charges. If you put it in water, it will not dissolve. Salt has charges. Carbon tetrachloride, CCl4, does not. So if you put salt in CCl4, it will not dissolve. Like dissolves like. The iodine will dissolve in the CCl4, the salt will dissolve in the water, but when you cross them up, they won't do that. The solubility of polar substances, again, depends on charges. And here's an example of ethanol, which is alcohol. Alcohol dissolves in water. And what happens is if you have something like an alcohol, this is ethyl alcohol, it has an OH group. The OH group has a little negative oxygen and a positive hydrogen. It's part of this molecule. And so what ends up happening is if you put this in water, this positive hydrogen is attracted to the water, and that's why alcohol, which while it's molecular, it has this OH group, which has a charge, so it will dissolve. Like dissolves like. Sugar dissolves in water as well, but notice what you have all over sugar rings. You have these OH groups, which you may remember from biology. Those OH groups have the same arrangement. You have this OH, and that's what allows them to dissolve in water. Now, if you mix two liquids, one without charges, one with charges, something like oil and water, oil has no charge, water is polar and has charges, so again, they don't mix. And many of you have seen that oil and water don't mix because the one has charges, the other does not. So non-polar oil will not interact with that polar water. Water itself has the hydrogen bonds and keeps the water from mixing with the non-polar molecules, and they have that attraction to one another. Now, another thing, so the nature, like dissolves like. Charges dissolve charges, no charges dissolve no charges. Another thing that will affect whether things dissolve is temperature. Generally, solids, as you heat them up, become more soluble. So for the most part, and there are a few exceptions, but in general, what ends up happening is you can dissolve more solid at a higher temperature, less at a lower temperature. So if you're trying to dissolve, say, salt in water, you'll find that more will dissolve at a higher temperature than at a lower temperature. Now, for an endothermic solid, like that ammonium nitrate and so forth, the temperature drops when the solute and solvent are mixed. Raising the temperature will increase the solubility. For an exothermic solid, if the temperature rises when the temperature of the solute and solvent are mixed, the temperature will decrease the solubility. So depending on whether it's an endo or exothermic solution, you can have some exceptions to that. But in general, recognize the rule. The higher the temperature, the more solids dissolve. Gases are less soluble at high temperatures than low temperatures. And again, this makes a little bit of sense too, because the gas particles, if you get them at a higher temperature, they're moving faster. It makes it easier for them to escape the liquid, and they escape off as a gas. So if you have, like a soda on a warm day, the CO2, it will go flat more quickly if you're outside, because the warmer temperature, the warmer soda will lose the CO2 more quickly than a cold soda. So again, the higher the temperature, the less gases are soluble, but the more solids are generally soluble. And then another thing which we mentioned in the very first slide on this section is pressure. The higher the pressure, the more gas you can dissolve. If I increase the pressure, I'm going to have more collisions with the surface, so I'm going to have more gas particles getting trapped. The more particles I have getting trapped, obviously the higher the solubility. If you take a soda, and again, that's the best example you've probably seen in your day-to-day life, if you open up that soda, you are lowering the pressure because they bottle soda under about 2 atmospheres of pressure with CO2 on top. The minute you lower the pressure, the CO2 escapes and you have that CO2 coming out. And again, just another example of this. The solubility of a gas versus pressure. The higher the pressure, the more it will dissolve. Now, things that will cause stuff to dissolve more quickly that will not necessarily affect the final amount, but these are kind of obvious and many of you have seen these. Crushing. If you had powdered sugar versus a sugar cube, the powdered sugar is going to dissolve more quickly. There's a greater surface area, more interaction between the solvent and the solute. Stirring. You've probably all made some sort of a powdered beverage where you're mixing something in, lemonade or Kool-Aid. And again, if you just let it sit there, it takes forever. But if you stir it, again, you get more interaction between the solute and solvent, so things will dissolve more quickly. Temperature also will increase the speed of dissolving. Now, it also affects how much, but it does definitely increase the speed, again, because the particles are moving faster. The faster they're moving, the more interaction between solute and solvent, so the faster things dissolve. So all three of these factors affect the area over which the solvent can come into contact with the solute and therefore help to speed up the dissolving. And again, just anything that will increase that surface area and that interaction will assist in that dissolving process. Here's just a chart of this whole process. Again, you'll see salt, the solubility increases as we go. And you have all these solids becoming more soluble as we go up. There are some exceptions. Here's one, the cerium sulfate. But for the most part, things become more soluble, or solids become more soluble as the temperature goes up.